Hi, I'm Max. I'm software engineer of Software Mention, and I'm also doing my master's in Utrecht University in Netherlands. And my research interests are mostly related to programming languages theory. And here in Software Mention, I work on the StarkNet team, and mostly working on Cairo developer tools. And today, I would like to talk about the topic, which is a bit of in the intersection of those two. It's a really important problem in a blockchain ecosystem, which is how to not lose money. But it won't be today about any investment strategies. Sorry if somebody expected that. Today, we'll talk about a fundamental problem or a feature, depends how you look at it, of the blockchains. So yeah, first we'll start with smart contracts. What is smart contract? How many of you heard this term? I expected many. So smart contract is some code. We write some code, some application, and we can put it on the blockchain. And it's all we have to understand. And those smart contracts can expose some functionalities to users. And, for example, can hold some assets. So, for example, we have smart contracts, a contract which holds some tokens, and users from outside world can request it to transfer those assets to other user of the blockchain. And what are the consequences of that? Consequences are smart contracts can hold critical assets. Here is some code of Ethereum wallet. It's just not important to understand. I just wanted to show you that if I do something like this, right now it's highly vulnerable. So basically here, we not validate the sender of the money properly, and anybody can steal your money, which is not the best scenario. So somebody can say, okay, everybody, like for traditional web, developers can as well make some mistakes and write bad code. The case is, if I write some code, for example, which handles bank, and it's incorrect. So for example, I don't know, I can send money I don't have. When somebody uses that, bank can revert it in some way. So maybe it will require some Fuzz, so additional phone calls, but at the end of the day, they can revert this and undo the damage. It is not the case on blockchains, because by design, those are not revertible. So every mistake of a developer is like exponentially extrapolated, which is kind of big deal. And we have to put extra care to make things right. So what we want to do, we don't want to cry and, I don't know, moan all day. We just want to look for possible solutions. First, we can try to read our code carefully. Of course, we don't have to do it ourselves. We can assign other people to do this perfectly. Those people are experts. And we basically call those audits. And if you give it this fancy name, everything is great. But it's basically still conveyed by humans. And there are many problems which can be related to that. Like they can just miss the mistakes as we did. It's cool to do that. I'm not saying it's bad. It's just we want to look on better stuff. Next, we can do testing. Testing is a kind of classic approach. So assume we have, for example, consider arbitrary problem of sorting an array. Like we have some numbers and you want to sort them. So when we would like to check it on doing testing, we just select one specific array and would execute it on our code, using our code. And at the end, we will just assert if the array is in sorted state. So it's as expected state. It's cool. It generally it's how we do it in Web2. And it gives decent guarantees. But we can do better. Yes, we can do better. We can look in something like fuzz testing. So instead of providing the expected answer, we can write code which validates an answer. So we have if still considering array sorting algorithm, we write a code which checks if array is sorted. This way, when when fast testing our code, we can generate like big number of arrays and put like each of them through our code, and at the end, check each of them if it's like sorted at the end. So this, we can see, can provide much stronger guarantees than traditional testing, but still there can still be some misses, like because for many cases, this number of possible inputs to the code can be infinite or like at least very big. And it's infeasible to like just test it each time or even once. And at the end of the spectrum, have formal verification, which is the holy grail here, because we could just assume input is any array and automatically, mathematically prove that output on our code which will be always a sorted array, which sounds very cool, but there are some problems, and I would like to get into first how it's done. Okay, so it isn't something I'm just taking from the hat. It's something that's actually adopted. And for example, Solidity, if you are familiar at least a little bit with Ethereum stack, on Solidity, if you download Solidity on your computer, it includes some kind of formal verification you can execute. And I know there's maybe a bit too much code to read, sorry for that, but I just wanted to show it, to give you a feeling of a real-world example. So here we have some function which takes an array and finds a maximum element from this array. So at the top of the function, we can see the code, which calculates this element and sets m to it. And at the end, we provide something which we call formal specification. What formal specification is? It's the way we define correctness of our code. Because it would be unreasonable to assume our computer will know what code being correct means. Okay, so here, what we do, we just iterate over the array and provide an assert. For each element of the array, we check if our maximum element is greater or equal than the element of the array. So we can assume it defines how maximum element, what maximum element of an array is. Okay. How right now we can take this formal specification and show with it like our code is correct, this code above. So we will get into a bit simpler example here. So we would like to look into a function which looks like this. It's very simple, just like for a purpose of demonstration. So here we have a function that takes one variable. It defines y variable, which is assigned to x. Defines z variable, which is assigned to some random value. And at the end, it increments x by 2. And our formal specification here is like x is greater than y. If somebody is good at looking at such stuff, he sees right now it's correct. Like it always happens, so this specification always be satisfied. But how to do it automatically? So computer can do it, not our poor, tired eyes. So okay, what we want to do is symbolic execution, which is a weird term, but what we want to do, we want to, instead of executing code on some values, we want to take our specification as a value and execute it backwards. So what does it mean? For this example, our formal specification was x is greater than y, so we start with value x is greater than y. And then we go upwards. So first, we can see like x is assigned to x plus 2, and we executed this assignment on our specification, and right now our specification is transformed to x plus 2 is greater than y. Sorry. And then we executed on one instruction upwards, and z is not included there, so it basically has no effect on it. And at the end, y is assigned to x, so we basically, what we do is replace y with x. And this is the final result. Does it make sense? Anybody has any questions here? Yeah.
You still have to include this x is bigger than y on the bottom, right?
Yeah, it has to be specified by developer. Yeah, it has, like, you have to define in some way what is correct, because computer cannot know. Like, you can write some. You might have as a developer any expectation about the code, but that's true. Any more questions here?
So you always have to go to some kind of a tautology to make a formal verification.
Can you repeat the question? Sorry.
Yeah, sure. So you have always to go through some sort of tautology to have a formal verification, because if you haven't y equals x here, you wouldn't have any reasons to believe that that code is correct.
We'll get in 1 second to that.
Okay.
Just like right now, just how we reduce that, it just makes sense. So here we can see our code is correct if this equation holds for any value of x.
What if x overflows?
Okay, this is an important question. And here, for the sake of example, we don't consider that. We just consider always uints are correct uints. You probably would like to include your formal specification at the end. Yeah, it's complicated to do that, to explain for everything and consider everything, but that's true. And I think if you go into official Ethereum docs, formal specification will include some examples of overflowing, because you can verify those as well. So does that make sense? If for any value of x, this will be satisfied, our code is correct. According to our formal specification we defined ourselves. Great. Of course, as Pavel mentioned before, if, for example, because if we look on this example, it's pretty obvious that it's always correct. Because if we increment x by 2, it will be always bigger than itself. But for example, if it would be y on the other side, it wouldn't be always true. So here, what we want to do is we would like to do it automatically, because those examples can sometimes be much more complicated and much bigger. So we cannot see it with our eyes. So there is one problem in mathematics and computer science, which is called satisfiability module of theories, which answers a bit similar question. We just find a value which satisfies a set of inequalities. Or just it's in generality, but in specific case, you just check if there is any value that satisfies inequality. So we want to use that. And tools that do that are called SMT, Satisfiability Module of Theory solvers. And there is lots of advancement in such tooling. For example, one of, and probably the most popular of them is from Microsoft. It's named Z3, and it's mostly built for formal verification purposes. And what SMT solver does, it takes a set of inequalities, which can be a bit more complicated because those can also include some logical formula stuff. But generally, it takes sets of inequalities and returns a value that satisfies any value. But we wanted to show that this is true for any value, not check if there any value that holds it, because it will be a bit similar to testing. Just look for one value that our code works, but we don't check if it works for all values. It's useless for us. So what we want to do right now is some small logic trick. We want to negate our value for our equations. So this way, we make our SMT solver to look for a counterexample for our code. And we hope it to fail, because if it fails, we pass the test, our code works. Does it make sense? Great. So it's perfect world. We don't have any more bugs, yeah? Why we started using it tomorrow? World is not perfect, yeah? We have problems here. So first, and the biggest one, if you do any kind of course on formal verification on university, first thing you learn is a lost battle, because we cannot do that for every code. It's proven mathematically, because that we cannot show, we cannot write a code that verifies if other code will always end. So we cannot generally verify our code. But there are some tricks we can do to provide very strong guarantees, which will be sufficient. But also for blockchains, we always also consider like finite executions, because we have a concept of a gas. So generally, it plays nicely with the concept of blockchain, which is good. That's why I want to use it there. Next problem is SMT solving is NP hard. It's very hard word to saying. It's very complex to calculate, and we don't have good algorithms to do that. We have some approaches, and there is like lots of work done in computer science in recent 20 years to make it as fast as possible, but generally it's still unfeasible for very large code bases. The thing is, for blockchains, those code bases aren't that big. We write like approach for blockchain, we generate like smaller modular smart contracts which interact with each other. So it's much easier to do so than, for example, some random Java code base which you can encounter somewhere else. So it's good. It also plays nicely with our approach and our problems. And the problem number 3, which was mentioned before, and also I think mentioned it briefly, we need to write those requirements. Which is generally harder than programming itself. Because I think I showed you before an example of formal specification of looking for a maximum value. So this specification we provide is kind of flaky. Because it doesn't check if the element which M is set to comes from the original array. So it could accept incorrect code. So and what we see here, it's a kind of problem, but still it can provide some guarantees. So as a summary of this talk and what the feeling about the formal verification I want to leave it with you, I want to leave in you, is like it's another tool which can help you mitigate the risk. And it's already adopted. Many projects which develop smart contract on blockchain use that. And you don't want to treat it as a holy grail that solves our problems. But we actually can use that, and it's usable. And it can provide you many additional guarantees about your code, which is great. And I think generally in security, we just want to mitigate the risk, because real world is so complicated that we cannot solve everything and have no problems anyway. I have no problems at all. Okay, that's it from me. If somebody has any questions, right now, it's a great time.
Okay, so when you talk about SMTs, they are really just like bounded to the inequalities, or does it cover like a set of logical operators, like AND and ORs?
So basically, I don't think I need that, but I can show that. Okay, never mind. Yeah, it's basically SMT. If somebody is familiar with some concepts from theoretical computer science, SMT is generalization of SAT. Yeah. So basically, it extends classical like SAT with some inequalities. So okay. it's stronger guarantee.
Okay, so yeah. So you could like just do a reduction from like just all logical operators to only inequalities. So you could like prove that SMT is also NP-hard from the SAT. Yeah, that's how we can prove it. Like, it's the easiest way. Yeah.
Hi. Hello. Thanks. I would like only to mention about another strategy of maybe it could be a solution to or to prevent which can be make something wrong in code of smart contract. I don't know if you're familiar with multi-signature wallets, when you can take another person to can say if this transaction is okay or not. So if something is wrong in in this transaction, you can take another person. If you take a multi-signature, or maybe you can make an extra clause or extra provision to take this dispute about this problem of executing, of doing of something in this smart contract. You can take it to another person, like institution. For example, Kleros. It is it is a decentralized application which is made to dispute resolutions. Yeah. It is some kind of alternative dispute resolutions in decentralized world. Thanks.
Yeah, that's true. That there are many different, like, because as mentioned, it's a big problem and a feature because it's hard to call it a problem of smart contracts because, like, if we wanted to do that, it's like what we wanted exactly. We don't want it to be reverted by anybody, at least by like some random entity. But on the other hand, it's a big problem, and there are many solutions to that. Like, I think, like, even like formal verification has many more flavors itself. I think, like I mentioned, like the most popular one and most, like, I don't know, from my perspective, a bit maybe interesting for general audience, but there are lots of stuff we can be done there, and those can include, like, as you mentioned, a bit more like human-based auditing, and as well as like using computer to help us.
Hello.
Hi.
Thank you. I've got a question about formal verification of that complex stuff, for example, as consensus of Ethereum 2.0. They someone, third-party service, provide them formal verification, but it's blow my mind how it's possible to verify so complex stuff as like that. Maybe you can explain into words how it's working.
But can you repeat your question? Sorry, because I'm not sure.
Yeah. I'm trying to understand how we can use formal verification for something more complex than that function. And as example, we can select, I don't know, a lot of things from Cardano or Ethereum consensus or any other stuff. Maybe you can explain into words how it's working.
Okay, generally I think, as I mentioned, those defining formal verification is often hard, like defining those guarantees. We can never expect it to be 100% correct because people develop those requirements. But generally, I'm not sure if I do exactly with a process how to do it because it's just like how writing code does. Like a bit on the other side, because instead of writing code, you write some like formal specification. And like in general, like it's something you do in your head when you write code, yeah? Because if you want to write code, you have to imagine how it wants you to act in specific scenarios. And then you have to provide constraints how you want to work. So I think the approach is like general approach to doing such complex things and like mathematics and programming. And I think most people use that. It's just like, okay, it's have adversary thinking. So you design some contract, and then you provide some, okay, I want it to only, to always, I don't know, to value of, for example, the number of tokens always be greater than 0. And then you come up with adversary. Adversary is an entity which can, like, you imagine to being like attacking your contract. And you design an attack, and then you update your formal specification to protect it. And then you go back again, adversary, attack, update, like the cycle. And it's how you do it. Like it's a process.
So if I just could add on that, I think like formal verification could be applied to larger contracts and more complex contracts, like in a manner of divide and conquer. So you take smaller problems that you have, like basic principles of your system, and try to break them, like Max said. And I think if you come up with a sufficient number of those principles, I think you will come up with a system that is able to protect your system pretty well from those flaws that might happen.
But how you can understand it's a pretty well, not behind? In that case, what's the difference behind testing and formal verification? Because I can't see the difference.
I see your point. Like generally, it always ends up on humans can make mistakes. So generally, okay, I can give you some examples here. If you devise, for example, if you devise formal specification, then if you modify the code, you can still check if it holds. Yeah. So basically, it's still like the game is the same as testing, but after, like for tests, if you want to write a test, you still have to devise the property. Here, you just have more expressive language to do so. I think is it. And if you like use this more expressive language, you can show it like for all of them, at least for majority. Like this is the problem of halting it. But that's I think getting into the weeds. But yeah, that's true. Like that's the problem here. Like we still have to write those requirements, and this can be bad. But I think it's better. It's easier to get into this game of adversary. And for example, it's sometimes a bit easier to have people who define them separately. It's also useful for testing as well. But here, I don't know. Like you can, if somebody else defines the constraints, the formal requirements, and somebody else is writing the code, it also can help because you can mitigate some stuff. But as it's a game of still human errors can encounter it. We can have a silver bullet here.
So my question is from the developer experience perspective. So let's assume that I know the formal verification and I know that I would like my program to be formally verified. So should I, from the beginning of the writing, just think about that it will be at some point formally verified? So probably more of a functional program, or can I just, write my Flaky code, my Flaky object-oriented code, and later it will just be formally verified?
I think I would approach it. I would try to define the specification, and then I write tests as well this way. I just write tests and write code, but
so it means that when I'm writing the tests, I'm also writing those specifications.
Yeah, I think like tests, okay, maybe to give you some context, like if you have a formal specification, you can use it to automatically generate tests. So like unit tests at the beginning. So, or you can also, for example, if you have this, if I go to this formula, so those are very closely related. It's just like, here you write your requirements in a more general way. Because, for example, if you have this equation, if you test it on random values, it would be equivalent to fuzz testing. So, and I read recently a paper which tries to create a SMT solver on GPU, which runs into thousands of threads and speeds up some stuff, but provides less strong guarantees. Yeah.
So, for example, if I have my code base and I submit into the formal verification, it means that the verifier will just try to come up with these requirements, right? And create those inequalities to check.
Yeah, like you have to write those asserts, like looking for the solidity, you have to write those asserts, and those equalities will be like a result of the symbolic execution because your formal verifier can do that.
But isn't it still relying on that people will just come up with the good requirements?
Yes, I said that. That's true. Like some people consider that simpler, and you can find a lot of mistakes this way. It can be proven. I think. It's like I said, there are different flavors of formal verification, but for example, you have methods to prove protocols, for example. You also have to, internet protocols, like those are deadlock-free, and you have to do the same for blockchains. And generally, those are kind of very well proven and good to finding small mistakes, for example, for hardware. It's heavy, if you look into careers on Apple or any company that does some hardware, they basically have always have some formal verification people because there it's heavily used because they can do lots of small mistakes there, and it's similar in blockchains.
So basically, from the developer experience, I think still, if you know that your code will be formally verified, you still need to think about it and to have those requirements, because if you just write the flaky code and assume that the verifier will just come up with the good assertions, it's basically as the audit, right?
Yeah, that's true. But if you if you have like it's, of course it's like it still collapses to like this classic like I have to have this nice example. It still collapses to it. Like people can make mistakes. It's just a method which can you expand on that and give people stronger tools to work with them. And this is the case because like many people find like if you maybe even of the level of the mind game, it's easier to look. Okay, how to define is correct might be easier than just looking at the code. Oh, it's correct or not? Yeah. And also audits. Like if you have audits, I think they're using like some formal constraints as well. Like they have some specification they want to check for, and some like often formal stuff. So basically, it always collapses to that. When you write software, you also like often first try to gather our requirements, and then you write the code.
Okay, thanks.
Any more questions? Oh, there was one question there.
So I have one question about how those solvers compute those results or verifies this statement. You mentioned about that they're using GPUs and threads on it to...
No, like just classical approach, I don't think it's GPU based, but I'm not expert on MTL server itself, so I just...
Is this some kind of simple brute force approach to check every possible solution, or is there some algorithm behind it that simplifies this?
Yeah, generally, there is no algorithm which works in general. So because it's NP hard. So I think if we had an algorithm for that, we could have much better things that like making our blockchain code secure. But there are some classes of such problems which often like occur in your world, which we can often simplify or make them faster. Yeah. So basically, it's often based on heuristics and developing them properly, so you can reduce some problems, make them simpler.
Okay, thank you.
Any more questions? Great. Okay, there's one more.
Yeah, so my question is like, is the theory behind this proving assumes that the code is being executed on one core in a single thread? How would that solver...
Okay, for example, I show you. Yes, it assumes that. But there are like, it's one of the techniques. For example, there are something like called temporal verification. Like if you heard the term TLA plus, maybe I have somebody on the list also heard that, which is used more for like multi-core stuff. And it's, for example, it has been used for verifying some network protocols that those are, for example, deadlock-free. It's a bit different, and it works more on automata theory. But generally, what it's there, you have like specific logic language, which is like kind of model language, model logic, and this logic includes some operators, which are like always or at some time, and you can write your properties there. So, for example, you can, I don't know, if you have some multi-threading problem, like 4 or 5 philosophers problem, you can model this problem, like your algorithm in this tool, and then write this formal specification. And for example, you can devise a formal specification that is like it's deadlock-free. And it actually is very good. Like if you play around with it, you can see like it's much easier to come up with specification that something is deadlock-free than to write a code that is deadlock-free. And those are also very heavily used for like networking and stuff like that. Okay. I think like last one question, or we can wrap up today talks. Okay, great. Thank you all then. At the end, I have some announcements. So first, It's the first meetup, but not last. We'll be holding next sessions, and you have doing something interesting, and it doesn't have to be strictly like technical. I think like if you have something interesting to show, feel free to reach us on Telegram or Twitter, and just like find our website and write an email. And we are welcome any talks in the future. So feel free to do that, and we'll much appreciate that if you do so, because it's always great to have other people tell what they're working on. And a bit unrelated to blockchains is if you want to take a photo, sorry, because I see you take a photo. If somebody wants to take a photo of that, you can do it right now. I think we generally accept, like not everything. I cannot promise you I accept everything, but if it will like, I think those talks today give you a general vibe what we are looking for, but you also would be happy to maybe expand it a little bit. So I think if you have an idea, just reach to us. Maybe we can either try to either say it's great, or maybe you can direct a little bit. Maybe this way we'll be fitting a bit more. But I think like I would say we are open for everything, and if you want to talk about something, feel free. Okay. And it's unrelated, but if somebody is into multimedia and on our streaming related stuff, we are doing a conference on multimedia streaming, because it's like other specialization of software mentioned. We are doing lots of stuff related to streaming. And if somebody is into that, as I said, feel free to join the conference. It will be in October this year. Okay, great, thank you then. We'll be here from some time, and probably like it's our to network. If somebody wants to talk about anything, feel free to take fresh beer and enjoy your time. And thank you once again for attending talks, and see you in the future. Probably this next meetup we aim for early autumn or something like September, October, I think, approximately. Okay, thank you.